So like I was saying before, rational functions you guys learned in algebra. All of this you have learned before. Nothing we're going over today is new to you. All right? That being said, what does the equation of a rational function look like? A rational function is a function in the form of a fraction with the variable in the denominator. So a rational function is written in the form f of x, right? That makes it a function, is equal to p of x over, whoopsies, p of x. What is going on? Oh my, there we go. X, q of x. Basically, p of x and q of x are polynomial functions where q of x cannot equal what? What is the one thing that you cannot have in that denominator? Yes, Sydney. Yes, exactly. Q of x equaling 0 creates an undefined moment on your graph, right? If we try to divide by 0, our calculator will say we have an error. It's an undefined equation when q of x is equal to 0. So we say q of x can never equal 0. One of the simplest rational functions is the reciprocal function f of x equals 1 over x. In algebra, we call this the parent function for our rational functions. We call this the parent function. And when we look over here to the left, this graph represents 1 over x. Does anyone remember what is one of the major attributes of a rational function's graph? What forces it to have this shape? They're actually invisible, the things I'm talking about. And it starts with A. What is a, yes, I even like left it on the screen. Do you see that? It says an asymptote right there below the whatever. Yes, one of, and I like to think of it as the main defining force behind a rational function's graph is its asymptote. Now, how many asymptotes do we have on this graph? Oh, not quite that many. Close though, Sydney. I think I see where your brain is going. You're thinking like the four quadrants. Right. There are two asymptotes. There are two asymptotes here. One along the x-axis. We call this a horizontal asymptote. Right? It's like the horizon. And its equation is y equals 0. We have a horizontal asymptote at y equals 0. We also have a vertical asymptote at x equals 0. Based on different transformations happening to this graph, these asymptotes will move. They will move. But this is our parent function. This is where they start. This is where they start off. And an asymptote, by definition, is a line which the graph, Normally, I would end the sentence with and does not touch, but that is not true for horizontal asymptote. Your graph can touch the horizontal asymptote. In this case, it doesn't, and in most cases, it doesn't. But it is possible for your graph to touch a horizontal asymptote. All that the horizontal asymptote, I'm so sorry, vertical. Jesus, vertical asymptote. No, I was right the first time. Horizontal. Oh my God, where is my brain today? Ugh. We can all cross a horizontal asymptote. All that the horizontal asymptote tells you is the end behavior. Where it's approaching on the end. That's why they say an asymptote is a line which your graph approaches. It will never touch a vertical asymptote. Never, ever, ever, ever. All right. In our little example to the right, the vertical asymptote is located where? Where is our vertical asymptote? Yes, good. Exactly. And I know that for some of you, and I don't know why, but some of you have a hard time locating asymptotes because they're not drawn explicitly on your graph. The best way that I know to describe how to find the asymptote is to look at the extremes. So if I'm looking at this graph and I'm trying to find the vertical asymptote, I notice that this graph on the top is ending just a little bit to the left, I'm sorry, the right of -3. And down here, it ends a little bit to the left of -3. So the line that is in the middle, the line that is between these two extremes is your asymptote. For some of us, it's super easy to find that line. And for some reason, it's very hard. Like when I was teaching algebra 2, I was seeing people draw like this. I was like, okay, what exactly are you drawing there? No, it's not -2. Okay. This is x equals -3. It's our vertical asymptote. What about our horizontal? Where is that horizontal asymptote located? Yes. Again, if you struggle to find your asymptote, look at the extremes of your graph. So we're trying to find the horizontal line. So we look, okay, the top portion of our graph ends here, or the ending drawn point is there. And it also has an arrow there. The midway line between these two ends is our asymptote. And this is y equals 1. Math Excel is going to give you problems like this and ask you to find the asymptotes. You are just going to have to do your best to try to find the average between the two ends of your graph, okay? And we will go over in a little bit how to find these asymptotes algebraically using our equations. But before we do that, we need to go over a few more attributes. Does anyone remember holes? Does anyone know how a hole, we're not reading this, don't read it, don't do it. How is a hole created? This right here is the hole. How is that created? From our equation. I guess you can read it. Somebody read it and tell me, how is a whole created? Yes. I love that you put it in your own words. Exactly. When you have a common factor between the numerator and the denominator, those common factors will cancel out, creating a whole, creating a removable discontinuity. It's a whole is like the slang word for it. Removable discontinuity or break in the graph. So in this little example here, we have x minus 2 over x minus 2 times x minus 1. We have a common factor between the numerator and the denominator. It will actually cancel out of our equation. It cancels out of our equation completely, creating a removable discontinuity. It's removed from the equation. And the thing is actually located at the zero of this factor. So you set this equal to 0, you add the 2 over, your whole is actually located at the x value of 2. If it hadn't canceled out, say this had been a different number, let's see, I don't know, plus 2, okay? Don't draw that because it's not. Pretend that had been a plus 2. What this x minus 2 would have created was another vertical asymptote. What this x minus 1 creates is a vertical asymptote. Because in our problem, our numerator is actually a minus 2, canceling it out, it no longer is a vertical asymptote. It instead turns into a whole, right? Because we have 2. If I was to plug 2 into this equation, 2 minus 2 is 0. I would be dividing by 0, which is not allowed. Remember, the denominator cannot be 0. So we still have to have a discontinuity here, but it's just no longer a vertical asymptote. All right. So now, I'm going to skip these steps. I'm going to come back to them in a second. These steps right here. I want to go over how to find a horizontal asymptote. This is the most forgotten part of algebra 2, I have to say. Like, from my experience, when I asked like previous students things about algebra 2, this seemed to be the thing that you just cannot remember. And I don't know why. Maybe because it's so weird. Who knows? But in order to find a horizontal asymptote, you always look at original function. Before you factor, before you cancel out wholes, before you do anything, look at the original function to find the horizontal asymptote. And in order to find it, you need to memorize this acronym. Bobo, Batten, eats CC. Does anyone remember this? Does anyone remember? Okay, let me break it down. Oh, you do? That's awesome, Samantha. I swear. First period, no one remembered it. Now here's the trick. Does anyone remember what Bobo stands for? Right, me. Does anyone remember what Bobo stands for? Yes, one of the letters does stand for bottom. I don't think so. Maybe. I'm pretty sure everyone learned this acronym, but maybe. This second B stands for bottom. What do you think this first B stands for? Yes, thanks. Oh my God. BOBO stands for bigger. We'll just uh, shorten that down to big. Bigger on bottom. What do you think that actually, well, I'll say O. What do you think that O stands for? It's not actually an O. Bigger on bottom. What is our asymptote? Yes. Bigger on bottom. Uh, make me anybody. Yes, big thing. Mm, not quite. I like how you're thinking though. Yes, Ava. Oh, that O is actually a zero. Your asymptote, if you have a bigger exponent on the bottom, your asymptote is y equals zero. Meaning, for example, if we had an x squared minus 4 over, I don't know, x cubed plus 3, we're looking at our exponents here, our leading terms exponent, or the degree of the polynomial, right? So we're looking at this leading terms exponent, it's a 2. We're looking at the denominator's leading term exponent, it's a 3. We have a bigger exponent on the bottom. Your asymptote is y equals 0. Next, we have bottom. What do you think that first B stands for? Or can you guess what BOT stands for? Yes, yes, guys. Big on top. So that's this one right here. That's a top one. I know it's out of order. I'm so sorry. But say we have bigger on top. So here I'm looking at my exponents. I have a bigger exponent on the top than I do the bottom. Do you know what the N stands for? No, 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 no. Close, kind of close though. It's not a number bigger than 0. Okay. You might not get this one. I'll just tell you. If we have a bigger exponent on the top, there is no, uh-oh, gosh, if it's bigger on top, there is no horizontal asymptote. Now, this is true. There isn't a horizontal asymptote, but technically this means there is something called a slant asymptote. But here in on-level printout, we are not worrying about our slant asymptote, okay? But just know if you're curious, yes, there is no horizontal asymptote, but there is a slanted asymptote. But again, we're not worrying about that slant asymptote. Now the last one, I will be super duper impressed. Oh, I didn't finish this problem. Oh my God. Well, I did kind of. Here, because I have a bigger exponent on top than I do the bottom, we say there is no horizontal asymptote. Okay, so the last one, eats DC. Do you remember what this means? Do you remember what the E stands for? No. Yes, exponent. What about the exponent? So far we've gone over bigger exponent on top, bigger exponent on bottom. What haven't we gone over yet? Yes, Lauren. Or the same. When exponents are the same, what you have to do is you divide the coefficients. So what I mean by this, let's do, whoops, 3x squared plus 2 over 2x squared minus 3. I guess I should numbers over again, huh? Notice I'm looking at my leading terms exponent, or the degree of the polynomial. I have a 2 as the exponent on top and a 2 as the exponent on the bottom. These exponents are the same, meaning I take the coefficients on the leading terms and I divide them to find my horizontal asymptote. So here, the exponent, or I'm sorry, the coefficient on the numerator is 3, and the coefficient on the denominator is 2. Therefore, I have a horizontal asymptote at 3/2. That's 1 point, in between 1 and 2, right? Any questions on finding the horizontal asymptote? Okay. So now we're going to try to put it all together. I'm going to do 2 problems, and if I have enough time, um, I'll do a third if you want me to. We'll see how. Number 1, these are the, by the way, these are the steps for finding the graph, the complete graph of a rational function. So the first thing we have to do, step 1, is rewrite the function in factored form. The first thing you do is factor everything and then simplify. Step 2 is to find the x-intercepts by finding the zeros of p of x. And if you recall, p of x is the numerator. So to find the x-intercepts, all you have to do is find the zeros of your numerator. To find the y-intercept, you find f of 0, meaning you plug 0 in for x. Step 4, find the vertical asymptote by finding the zeros of q of x. Remember, that's what I was talking about right up here. The zeros of the denominator create your vertical asymptote. Then you find your horizontal asymptote. Technically, finding the horizontal asymptotes can be done at any time, but we like to do it at the end. Or I personally like to do it at the end. Again, doesn't matter when you do it. Okay, so let's try to do this all together. I'll do an easy one first. Does anyone know why this number 1 is considered an easy one? Or can you take a guess at why it's considered an easy one? Yeah, no coefficient sure helps. What else? What is different about this number one versus this number five that I'll do? Uh-oh, there we go. This number five that I'm going to do next. No exponent, meaning I won't have to what? Look at our first step. What do I not have to do in number one? No, I'll need to find a horizontal asymptote. Look at step one. What does step one tell us to do? Right before the word simplify. Factor. Yes. Look, guys. I can't do that. It's already done. I have a linear factor over a linear factor. There is no way to factor these. They're already for us. Great news. I can move on. Everything's factored here. I don't have to worry about it. Step two. Find the x-intercept by finding the zeros of the numerator. So first thing I'm going to do, I'm going to find the x-intercept. Wow, it changed my color, really. X-intercept. We look at our numerator and we're trying to take that factor and find the zero for that factor. How do we find a zero again? How do we take a factor and find a zero? Yeah, wonderful. Easy peasy. Set it equal to zero. Subtract the 1 over. Our x-intercept is -1. Now, right now, the way I have it written, x equals -1, that's technically a line on the graph, right? That's technically a line through -1. Our x-intercept is not a line. X-intercept is points. So how should I write the x-intercept in my little table over here? What should I write down? Last class really struggled with this too, like super hard. Should I just put x equals -1, which technically that tells me I'm drawing a line. Don't draw this. I'm drawing this. Is that what I should be doing? Well, actually, an asymptote is fine. Should I just be drawing that line? Is that what an asymptote is? Guys, how do we represent x-intercepts on a graph? Yes, it's a point on the graph, meaning we have to write down a coordinate point. The x value is -1, and the y value, because it's the x-intercept, the y value is always 0. And I go ahead and I place that point on my graph. -1, 0. Whew. Isabella, you should be like proud. No one in first grade at all got that. And I even end up having to write like -1 comma and then I left the zero blank and I'm like, what goes there? And no one thinks, all right. So now what was our next? Let's see. So we've done one, we didn't really need to do it. We've done two. Now step three, is finding the y-intercept by plugging 0 in for x. So let's do it. I'm going to plug a 0 in, and I'm going to plug a 0 in. Right, this makes sense. We're trying to figure out when x is 0, what is your y value? This will be the y-intercept. And this simplifies down to negative 1/5. Can anyone tell me how this is written on our little table to the right here? How should I write this? Yes, you guys are making Isabella do all of the hard work here. This time x is 0 and y is -5. And that's not a very pretty point to graph. It's about a fifth of the way between 0 and -1. You kind of have to approximate where it is on the graph. Okay, next step. We've done 3, now 4. Find the vertical asymptotes by finding the zeros of the denominator. So we take our denominator, which in this case is x minus 5, and how do we find the 0 for that factor? Somebody other than Isabella. How do I find the 0 for this factor? Man, this coffee is hitting me hard. Yeah, Lauren, exactly. You set it equal to 0, and you add the 5 over. So here, our vertical asymptote is at x equals 5. And I graphed that on my graph. Let's see, 1, 2, 3, 4, 5. It's really, I should do something other than green because I think that you guys have a hard time seeing that. 1, 2, 3, 4, 5. This is the line x equals 5. That's my asymptote. And remember, my graph will never, ever, ever touch that line. Ever. It shapes my graph. My graph goes towards it infinitely, but never touches it. What is our last step? I think it's horizontal asymptote. Yes. All right. So now for the fun stuff. Oops. How do we find the horizontal asymptote? What do we look at to find our horizontal asymptote? Yes, Kate. We look at our original function, and what acronym do we say in our head? Which which part of our full acronym is true in this case? Remember, our full acronym is BOFO, BOM, CC. Yes, Lauren. Looking at the equation, we may not see any exponents, but we know on x's with no exponents, there's actually an invisible 1. So I have a 1 exponent over a 1 exponent. This means exponents are the same. What do we do in this case? What do we do? Yes, divide coefficients. Now I look at my leading term. Okay, there aren't any coefficients, but we also know that when there aren't coefficients, there's always an invisible 1. So here, my horizontal asymptote is 1 over 1, which just simplifies to 1, meaning I have a horizontal asymptote at y equals 1. Also, side note, are there any holes on this graph? Remember, right, Lauren, yes. Remember, holes are created when you have a like factor between the numerator and the denominator. Clearly here, we don't have a like factor, therefore, there are no holes. No holes were created in the making of this. Okay, so now we want to finish drawing our graph. Normally, if we were in person, I would say I need at least 3 points. That's my normal. I need at least 3 points. And also normally, if we were in person, I would say find it by hand. You need to find another perfect point by plugging in x values and hoping that you get a whole number y value. But because we're not in person, what you can do is you can use your calculator. So I'm going to take my calculator and I'm going to plug in this equation. If my calculator would ever turn on, holy crap. Okay. And I go to y equals and I'm going to put this equation in. Now this is something that you could have also done at the beginning of this problem if you wanted to make sure that you were doing everything correctly. So we have an x plus 1 over an x plus minus 5. And yeah, it's useful to look at the graph, but I think more useful in our case is to go right to your table. We're just trying to find one more perfect point. And look, I can see I have the negative 1, 0. That was my x-intercept, so I know I did that right. Let's find some more. And to be honest, I'm honestly trying to look for a perfect point that would create the other half of my line, the other half of my graph. Right now, I just have this portion of my graph. I am looking to create a mirror image of it, if you recall, on the diagonal of this lower half of my graph. So I'm looking for a more positive x value. Let's see. 4, negative 5. Nope, that's still on the portion of the graph I already have. Let's go past it. Okay, 6, 7. That should be useful. Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Right there. And of course, you could graph more points if you want. We have 7, 4 as well. 1, 2, 3, 4. But as long as you have 3 points, that's what I care about. And you're good to go. It doesn't have to be pretty. All I need are the vertical asymptote, horizontal asymptote, 3 points, and also any holes if there are any. But in this case, we have no holes. Okay, so now for the domain and range. What is our domain of this graph? I know these are long notes. I'm so sorry. And I'm sure I've lost you at this point. But you are starting at negative infinity, yes. When or where is your first stopping point? When does the line of your graph stop? Going left to right. When do you have to pick up your pen? If I'm tracing left to right, when do I have to pick up my pen to start my graph up again? Oh my goodness. People, are you still here? What can X not be is a better question. What can X not be? What can you not have for X? 5, right? You cannot have 5. Uh, you can have more than 5. Remember, we're having to pick up our pen to go to the other side of 5, but it's still continuing over there. That's fine. We just literally cannot have 5. And that's our domain. That's it. All you have to do is say that X cannot be your asymptote, your vertical asymptote. So knowing that, what do you think the range is? What do you think the range is? Yes, Sydney. Y such that Y cannot equal 1. So this was our vertical asymptote. This is our horizontal asymptote. I honestly love rational functions because the domain and range is so easy. Just easy. X is not the vertical asymptote and Y is not the horizontal asymptote. Any questions on this graph? Okay. I don't know why, but this is taking a lot longer than first period. I almost finished early in first period, but I do have one more problem I want to go over. This is the big, all right. This is the harder problem only because it isn't already factored for you. So step number one, factor everything. And I'm going to try to go a little bit quicker through this one so I do finish on time. So I'm not going to ask as many questions. But first things first, we have to factor everything. So the numerator is already factored. It's a linear factor. I'm good to go. The denominator, however, is the quadratic. I need to factor this. Again, you can factor however you want. I'm going to factor the x method. So up top goes 6, and the bottom goes -5. What multiplies to be 6, but adds to be 5? Yes. You already know what I'm going to ask you, right, guys? -3 and -2. And these are my true factors because I do not have an a value. So I rewrite this as x minus 3 over x minus 3, x minus 2. Uh-oh. What do you notice? What do you guys notice? Yes, you can cancel a factor, which we should go ahead and do. You want to cancel that whole out immediately. This is what the simplifying was in that step number one, factor and simplify. This is the simplifying. Go ahead and cancel out that x minus 3, and you're left with f of x equals 1 over x minus 2. Now, what does that canceling create in our graph? What is now created because we canceled out that factor? Yes, we now have a whole. A whole, which x value is 3. Now, is a whole a line on a graph? Should I draw a line for this whole on my graph? No, no. Good. A whole is a point on a graph. Unfortunately, this is only the x value of the point. So if I were to go over here, right, I'm trying to write down this whole. What do I also need? What do I also need if I'm trying to plot this whole? this point on my graph. Oh my gosh, a y value. Does anyone know how we find y values given an x value? What do you do? If I know the x value is 3, how do I find the y value? I know why. This is like the most forgotten concept of all time in math. And I feel like they drilled and killed this in Algebra 1. How, if you know what I tell you, how do you find the value? Oh, I said I wasn't going to answer a lot of questions. Yes, Colton. Oh, yes. You plug the x into your equation to find the y value. Yes. Now, I'm not going to plug it into the original because if I plugged it into the original, I would get an error, right? Because I would technically be dividing by 0. So we're going to plug it into this simplified form. 1 over 3 minus 2. 3 minus 2 is 1. Oh, I guess I should have written y equals. So sorry. So when our x value is 3, our y value is 1. I don't think I'm going to finish this problem in time. So we're going to plot the hole at 3, 1. 1, 2, 3, 1. You represent a hole with an open circle. It's a removable discontinuity on your graph. Then let's go ahead and do the steps like they told us, or keep doing the steps like they told us on the first page of our notes. Step 1 was to factor and simplify. We did it. Step 2, what was it? I think it was to find the x-intercept. Yeah, x-intercept. We find the x-intercepts. Why won't it change color? We find the x-intercepts by plugging or by finding the zeros of our numerator. Again, we're looking at the simplified form. What do you notice about the numerator though? It doesn't have a what? What does our numerator not have? That it would need to have to create a 0. My goodness. Okay. What is in the numerator right now of f of x, of our simplified form? What's in the numerator? A 1. It's a constant. A constant does not create an x-intercept on our graph. An x in our numerator is what creates a 0. Because there is no variable in the x or in the numerator, there is no x, x. So we write because no variable in numerator, there is no x-intercept. So over here in our little table, we write none. So now we're going to go ahead and find our y-intercept. Remember, our y-intercepts are found by plugging 0 into our x values. Now I'm going to use my simplified form and plug 0 in for x. And this simplifies down to -1/2. So my y-intercept is 0, comma, negative 1/2. And I'll go ahead and plot that point. 0, negative 1/2. Then for my vertical asymptote, remember, vertical asymptote is created by these zeros in the denominator. So the only factor I have in the denominator in my simplified form is x minus 2. So to find the 0 for that factor, you just set it equal to 0, and you add it to it. So our vertical asymptote is at x equals negative, or sorry, x equals 2. So I'm going to go ahead and draw that line. Oh, that doesn't show up well. Let's do pink. And this is the line x equals 2. Then my horizontal asymptote, remember, is when we look at the original and we ask ourselves about the exponents. Do I have bigger on top, bigger on bottom, or are the exponents the same? In this case, we have bigger on bottom, which means I have the asymptote y equals 0, which now makes sense why there are no x-intercepts, because I have an asymptote literally lying on the x-axis. So now we just need to find at least one more perfect point. Remembering, we can just plug this in, and I'm going to plug in the whole equation, x minus 3 x squared minus 5x plus 6. And I'm going to look in my table, and I have a 1 negative. That's this point right here. And then I have this point. I'm going to create, whoa, didn't even go through the point. Okay. I'm going to create, why did this being so difficult today? I'm going to create my graph. Again, it doesn't need to be pretty. I just need to know what your graph looks like. And then we find the domain and range. Our domain is everything except the asymptote, but in this case, it also cannot equal the x value of the whole. So not only can it not be 2, right, our vertical asymptote, it can also not be the x value of the whole, which is 3. And then our range, our y cannot equal, again, the asymptote, but it also cannot equal the y value of the whole. So this was our vertical asymptote. This was our horizontal asymptote, and this was our whole. And we're done.